some slides, but I also can move to a blackboard. Like I've got a blackboard ready, so if I can deviate in any way from whatever talk plan I had, no problem. So at the moment, okay, let me just start by sharing some slides. Share screen, there you go. I want this one. Share. And I go to full screen mode. Right, so I have two affiliations, in fact. So I'm at the University of Oxford, where in Department of Computer Science, we've built out a very big group called the Quantum Group, very original name, of course. And we're more than 50 people there, but I'm also affiliated with Cambridge Quantum Computing, which is a quantum computing company. I mean, as the name says, originally based in Cambridge, but at the moment, actually, as if next week or so, there will be Oxford offices of Cambridge Quantum Computing, which I also will be leading. And we start with a team specifically dedicated to what I'm now talking about. Goes without saying, they also have teams in Oxford, and as it turns out, the one who's heading the team in Oxford should be somewhere here in my house, but I don't see him in this is my pub where I work. It's sort of a music studio too. It's a music studio, and I mean, you can't really see it because I've got to do my screen sharing. So okay, let's just stop the sharing for a while. There you go. Stop screen sharing. How do I do this again? Okay, it doesn't matter. I'm not going to do this. I can do this later. But so one of the skeletons in the back has his face, but he may actually walk in any minute during the talk. And then the reason I'm saying this is he's leading the software team. He's leading the software team in Cambridge Quantum Computing, and maybe you've got some questions for him too about the sort of stuff they are doing, because the sort of stuff they are doing is also based on the sort of work I'm going to talk about here. So they're mainly working on quantum compilers there and related quantum software. And if you're interested in jobs in quantum industry and all that, he's also a person who can answer the questions there. So I hope he's going to walk in before the end of the talk. Okay, let me start with my, okay, there is the thing I want to do. So stop share, doesn't really matter. Yeah, as you see. So some of these people there, like, are people I work with, so I will introduce them when the time is there. Okay, so now I'm going to share again. Share screen, going back to my slides. There you go. Share. Okay, right. So let's start with this story. So this story goes back to 2008 at the University of Oxford here. So there was three people there. They happened to be in the same department, and they happened to be sitting in the same corridors too. So this was one person, and this person knew about what I call grammar algebra. So what is grammar algebra? It's, I mean, you see some symbols there on the right. Grammar algebra is a sort of stuff which you would associate the name Chomsky with. There's also other people who worked on that, mainly people like Lambeck and Montague. And these are algebraic systems, symbolic systems. And what they do for you is they tell you when you string a bunch of words together, which have a particular grammatical type, when they actually come together as a meaningful whole. So what sort of words you can actually put together in order to form a meaningful whole. So for example, you put a noun and then a transitive verb and then a noun, like Alice hates Bob. That's a meaningful whole. And this sort of bit of algebra, specifically the calculation you see there, tells you that Alice hates Bob is a meaningful whole. I mean, I'm not going to go into detail at that point. If somebody likes to hear more about this, I can go to the blackboard and try to explain that, how this works. It's very easy. But let me just continue the story. For now, you just have to assume something like that exists. And this exists for like a very long time. This goes back to 80 years and even more, that people start to come up with these algebraic systems which told you when a bunch of words make a meaningful whole. So now coming to much closer today to modern NLP. So there was somebody else, Steve Clark. And he knew about vector embeddings, which of course are now very well known and very famous, and because they're the core of machine learning and all that. So he knew about that when that stuff was starting. So he knew how to represent meanings of stuff in vector spaces, and how to compare meanings when they are closely related and things like that. That's sort of the stuff Steve was doing. I mean, then there was me, and I knew something which was called categorical quantum mechanics. So if you ever hear about category theory, so we basically recast quantum mechanics in purely category theoretic terms. But in other words, it's actually recasting quantum mechanics in purely diagrammatic terms. So I mean, a few years ago, Alex Kissinger and I, we wrote a book about it. It's a very big book, as you can see, 900 pages. It's full of pictures. It's basically what we started teaching as the quantum computing course 7 years by now ago in the computer science department. I mean, this is still the one which is being given because Alex is giving this now since starting this, was it last year or this year? Oh, starting this year, actually. Yeah, it's the first time he's teaching it now. So yeah, that's our course. It's a full course in quantum computing, but it uses like pictorial language. And one instance of this, which some people may have heard about because it's now becoming quite popular, is ZX calculus. You'll see a little bit about that later. I'm not going to go into anything there, but this is part of what you find in this book. So that's categorical quantum mechanics. Okay, why did we do this? Like I thought it was much better to have quantum mechanics in a form that is pictures, because I mean, it's kind of nice. Another way why we did this is because this goes back a very long time to Schrödinger in the 1930s, who believed that the core of quantum theory, the real soul of quantum theory, was what happens if you put systems together. So you take two systems and you put them together. And what we start to understand was that the way to axiomatically capture this idea of bringing systems together, you don't do with symbolic logic, but you do with pictures. It's really, I mean, I'll explain this in one of the following slides, how this works. But it's sort of, think of it as a new kind of maths which embraces composing things. It's a new kind of math which embraces, it's the logic of composing things. That's really what it is, these diagrams. And that's why it's so appropriate for quantum. And for something else, as I will explain now. So let's forget about the third person for now. Let's think about these two persons first. So on the one hand, you got something which is about grammar, and which tells you when you put things together. So I'm composing words here. So I'm talking already about composition again. If you compose words together, this tells you when the whole forms a meaningful whole. But what is the meaning of that meaningful whole? It just tells you that you obtain a meaningful whole, but it doesn't tell you what the meaning is of that meaningful whole, right? So the vector space NLP representations, what do they do? They tell you how to assign a meaning of, as in a vector space, to something. Now, what you want to do and what we humans do is put these things together. We put words after each other, and that forms the meaning as a whole of, say, a sentence. How do you do this? How do you compute that meaning of the whole, given the meaning of the parts? That's a challenge. Turns out there was no something like that. Nothing like that existed. Nobody had come up with some algorithm, if you want, or some theory which tells you what is the meaning of the whole, giving the meaning of the parts. So we try to then combine these two systems. They look, of course, very different. On the one hand, you got a piece of algebra. On the other hand, you got like just vectors living in a vector space. Turns out how you combine them mathematically, and this is also the answer to the question, if you want to why there are no dictionaries for sentences for us humans. If we hear a sentence we never heard before, then we understand it, provided we understand the words. We don't need a dictionary for every possible sentence that exists in the world, because we form that sentences. So how do we do that? This is how we do that. We use categorical quantum mechanics. I mean, this may sound crazy, but it just turns out to be the case that the sort of most compact and smallest formalism that combines these two aspects, this grammar algebra and vector space meanings, are exactly these diagrams of categorical quantum mechanics. Let me start to give you a hint here. So here you see a diagram, And this diagram could be a diagram in categorical quantum mechanics of physics, or it could be a computation of the meaning of a sentence. It could be both things. So in the case of physics, you see these three words here: Alice, H, Bob. So you can think of Alice as a physical system, a qubit, the state of a physical system. Think of Bob as the state of a physical system. Now H, you see the word H has three wires coming out, because we read the diagrams from top to bottom here. We read them from top to bottom. So H is a state of three systems. The fact that three wires are coming out, you have to think of it as a state of three physical systems. And what's happening here is like the state Alice is in some way connected with one of these systems of the state H, and the state Bob is in some way connected with one of the systems of the state H, and then something comes out as a whole. There's actually only one output wire to the whole thing. In a way, physicists would call this a double teleportation. They never really do that, but that's really what it is. So you have two things like Alice and Bob, you teleport them through H into the big wire. That's a physical reading of that. And if you read the categorical quantum mechanics book, our book, then that's what you would actually think of this. This is how you would interpret this thing. Now, so this is the physics side. Now we can also interpret this purely in terms of language, exactly the same thing. And so the top part, which is now in the red box, these you have to think of as vectors representing the meaning of Alice, a vector representing the meaning of H, a vector representing the meaning of Bob. And then the bit of the bottom is the more interesting thing. That's an alternative representation of the grammar algebra I was talking about. I show this as a bunch of symbolic strings. Let me go a few slides back. Here you see on top, you see this calculation with some -1 here and there. But it turns out that this particular calculation is equivalent to this picture. I can actually show this on a black. Maybe, okay, I'm going to show this on a blackboard because this is so important that I should show this on a blackboard. I'm going to go through this argument again. I'll move the camera a bit closer so you can see it better. Come on, camera, follow me, camera. We're gonna go there, so I can write on the blackboard. Okay, be careful, there's a lot of cables here. Let me see, I think the camera is kind of well placed now. Let me look at the little screen. Yeah, camera is well placed. I move the microphone so you can hear me. Everybody can hear and see me? Yes?
Yeah.
Yeah.
Maybe
okay,
it would be helpful to stop sharing the screen so your own enlargement. Yeah.
Of course. Yeah, that was part of the plan that I kind of forgot. There, good.
Yeah, good now.
That's better. So let me go to exactly the same point because it's really important. So I'll draw the same thing. So this is Alice. So Alice, and you really think of this as the meaning of Alice. So whatever it is, like whatever you find in a dictionary, a vector representation that people use now in word embodings, same thing. Here you got Bob. And then basically there is this third thing, which is some verb, in this case hates. And the way you think of this is that the meaning of Alice sort of flows through this wire in H. The meaning of Bob flows through this wire in H. H takes up these two words and spits out the meaning of the sentence. Now, an alternative way to do this symbolically, and this is how people do this with these grammar algebras, and the particular grammar algebra I'm going to talk about here is called pre-groups. So you know probably what a group is. So this is a group with the word pre in front. So I got group, then I got the word pre in front. So it's something weaker than a group. What is it weaker than a group? That if I've got a symbol, say n, then I can have an inverse at this side, or I can have an inverse at this side. So I've got two different sided inverses. That's really the idea here. So let me now show what is the corresponding bit of algebra to that thing. So you got a bunch of symbols, and these symbols represent grammatical types. So for example, one symbol.
Can you maybe adjust people saying that it's hard to see the board? Maybe there's some too much glare on the screen.
Oh, is there too much glare?
Yeah.
Is this better?
Well, yeah, that should be better.
Yeah.
Yeah, now it's good, yeah.
Yeah, okay. So maybe I should use a different color. So this is noun. So noun is a grammatical type, and it's sort of a basic symbol in my language. Another basic symbol in my language would be language, as in the grammar language, would be sentence, a type of sentence. So a noun is a thing which makes sense in its own right, like a word or a noun phrase. A sentence is a thing which makes sense in its own right. Something which doesn't make sense in its own right is, for example, a transitive verb. If you just say a transitive verb on its own, it doesn't really mean anything. Like, hey, if you say the word hate, like who hates who, it doesn't mean anything. It needs a subject and an object in order to produce meaning. The way you express this is that a transitive verb is some sort of composite. It wants to be a sentence, so there is a sentence in the middle. It wants to be a sentence, but it needs a noun on the left, which we indicate by putting a -1 there, and it needs a noun on the right, which we indicate by putting a -1 there. And then, so I got a noun, transitive verb, noun here. So these are these symbols. These are the symbols. Now, in the usual combination in maths, you would do, oh, this is n-1, so we scratch this. This is n-1, so we scratch this. And then this one remains. But there is sort of a nicer, more elegant way of writing this. You say these two symbols, instead of crashing them out, they annihilate each other. These two symbols, they annihilate each other. Sentence doesn't get annihilated, moves through. And you see sort of the wire structure I get here is exactly the same as the wire structure I get here. So that's what I'm saying, that this wire structure is actually is corresponding to this symbolic calculation. So it's really this entire calculation, including the sort of canceling out of things, that is really represented into this wire diagram. But then what we do after we do this calculation is we don't think of these wires anymore as a calculation. We really think of them as stuff like pipes in which information can flow. So we put these vectors here. And so Alice can flow through these two H, Bob can flow through these two H. They can interact in H together. And the meaning of the whole thing is spit out. So I think that's sort of a key part of this sort of grammar algebra to teach you how our sentences well formed suddenly becomes a picture like this. And then as a physical system for people, so in teleportation, you would think of this as a state, and this actually is something which is part of a measurement. This part of a measurement, and by measuring these two systems together, actually the content of this state and this state in some way interact with the content of this and produces something. And that's really teleportation. Whatever information is here moves from here there, whatever information is here moves from here there. That's what physicists call quantum teleportation. So the same picture has both this physical meaning, and it also gives like a direct corresponding thing to this grammar algebra, but not just being about grammar anymore, also being about meaning. I think I'm going to now go back to my slides. Yeah, I'm going back to my slides. So I'm going to start chatting again. I think it was worth to do this on a blackboard rather than just say this. Right, here we are. So that's just what I said. That's what I was saying. Oh, what did I just do? Okay. So the top part are these meanings. The bottom part was this grammatical structure. And together, we think of this as the computation of the meaning of the whole thing, where these wires actually force these things to interact. Okay, so this was in this paper, Mathematical Foundations for a Compositional Distributional Model of Meaning. This is sort of a later version. We started doing this in 2008. And the idea was really to combine meaning and grammar together in one formalism. And the formalism looks exactly like I just showed you. So now I'm going to try to, so how many people here know a little bit of quantum physics? Or have ever seen a course on quantum physics? I need a guess or an estimate, not a precise number.
Someone raise a hand. Okay, wait, I will let him talk.
Not everybody.
I think a lot of people should know what quantum is.
A little bit, okay. So it's just like what words. So because what I'm doing here is I'm starting to use some typical quantum mechanical notation to explain how meanings in language interact. But even if you don't know quantum, you can kind of slightly ignore the notation and just listen to what I say. So just like I was saying, like the meaning of a noun, think of it as a state. You can think of this as a state in a computer too, the state of some data in a computer. That's the meaning of something like a noun. So here I've got the word hat. Now, what I'm trying to figure out here, what is the meaning of black hat? So black hat is a noun, and you have an adjective applied to that noun. So what does an adjective do? It sort of modifies hat from being like unspecified in color to being specified in color. So it's something that modifies. So it's like a function. It takes hat and it produces a black hat. If we weren't talking about a hat, but I bought a cat, then it takes the cat and makes it black. So so it's more like a function which takes a noun and then returns a noun. So in pictures, we can represent this like this. Black hat is hat, which is a state, and then this box with an input and an output is something you can think of as a function. Now, one can be like a bit clever about this, and it turns out, I mean, I'm not going to do this one explicitly. It is something you can explain explicitly in a model with sets or with vector spaces, doesn't matter. So something like that, some picture where you apply something like that, some functional application can also be written like this. Maybe computer scientists who ever heard about currying, it's something like this which is happening here. So you can actually think of black instead of a function with an input and an output as a state on two systems, like with two outputs. And then there is something which combines one of the outputs with the noun input. This is literally a teleportation diagram. This is literally what people would call a teleportation. You take hat, and then you use, and then you got these two system state black, and then this upside down two system state, which we usually call a two system effect, which I call bell. And this allows like to hat to flow through these two system states. I mean, like I indicated in this picture here, hat can really flow across this wire. And this wire actually is a very formal thing. In the way we represent quantum mechanics, these wires are purely formal things. I mean, they're formal and in the sense that they're purely topological objects, which you can think of as wires. And then if you look at it like this, so you see this dotted line now, this is sort of showing how things inside this black thing there, this black box, it looks inside like that. And then this bell thing just became this cup-shaped wire. So if you yank that wire, you get exactly like hat with black applied. So it's just a different way to write the same things. And I mean, this is sort of symbolic representation. And this is exactly the same way. I'm now going to go quick. So you can think the same way, like here, you got Alice and Bob. You got two nouns, and you can think of hates as a function applied to it. You think of hates as a function applied to Alice and Bob, and then modifies Alice and Bob. How does it modify Alice and Bob? It modifies Alice and Bob from Alice and Bob having nothing to do with each other, nothing at all. Oh, I should bring my camera. My camera is still on the blackboard. Yeah, I mean, you need an assistant for this sort of kind of talks if you're going to run around with cameras and stuff. You should need an assistant, or you need two cameras, which you can switch, but then you forget to switch them anyway, like I forget to put off the screen sharing, so it doesn't really matter. Anyway, yeah, okay, here we are with two cameras, with the camera here. So, yeah, so H, you can think of a function applied to Alice and Bob, and then changes Alice and Bob from having nothing to do with each other, because if you put this Alice and Bob side by side, I mean, there's nothing relating them. They are just two names. But then by applying hates to it, suddenly they become very related, in the sense that one hates the other. Maybe the other one loves. That we don't know. We don't know Bob's perception of Alice. We just know that Alice doesn't like Bob very much. That's what we learn, and that's how the two states, Alice and Bob, change. They become entangled. They become entangled with each other in the relation, entangled in the sense of hate. So you can use quantum type of words here, and then with a similar trick like before, you can turn this in this picture. So that's just a different way to explain how you end up with this diagram in a sort of more physicsy language. Anyway, what you can do now is you got these computations of meaning of sentences. So what I depict here is actually an inner product. So I want to compute whether Alice hates Bob is closely related to Alice does not like Bob. So I can compute the meaning of Alice hates Bob in the way I just explained. I can compute the meaning of Alice does not like Bob, and then I take an inner product. I take an inner product, and if these two are closely related, then the inner product should be large. If the two have nothing to do with each other, then you would expect this to be small. So this is a way to compare sentence meanings by computing. That's why in the first place you want to compute these meanings to then compare. So long before that, 20 years ago, one of the things people were very proud about was using this vector representation to actually figure out which words are synonymous, because it allows you to figure out synonyms in the sense that they have very large inner products because they're pretty much the same. And this now extends this to sentences. Okay, so that's the thing we did. I mean, this got some attentions. Obviously, if you use quantum to do something in language, you become branded like some sort of crackpot, and they call me a quantum linguist or stuff like that. They call this thing quantum linguist. But we weren't thinking about this as anything to do with quantum. Just we happened to use that formalism, which we had done for Cairo quantum mechanics, which ended up being around, but which I try to explain to you is just a very natural way to combine meaning and grammar. It just felt very natural to do it, even if we would have nothing to do. Even if we as humanity wouldn't have known about quantum mechanics at all, we may still have come up with this as a way to combine meaning as grammar and grammar, right? So I mean, once you start playing this, you can come up with some more interesting ideas, like instead of like a thing. So here we got a sentence like she who hates Bob. So for Bob and hates, these are things you could actually empirically establish. That's how people do this now. They establish these meanings empirically. And that's how you establish these vector embeddings people talk a lot about, and that's what people do in machine learning. Now the word who is not something you're going to learn empirically, like who. Who has some sort of logical feel to it. And so what we then figured out is how to form who in a more logically motivated way. So we opened the Coecke quantum mechanics book again, and we found these things inside. And we said, okay, that's really the right way to do who. So what are these things I'm depicting here? These are things we call spiders. So they're the most crucial thing in our description of quantum mechanics now. These things called spiders. So they look like this. We represent them by a dot with some input legs, with some output legs. But ultimately, they are summations of basis vectors. So they're a generalization of the concept of a wire. Now you should think a bit philosophical about what is a wire doing. A wire is a thing which has two ends. Yeah, I mean two ends that are connected. And if I pull at one end of a wire, the other end moves. If I pull at the other end of the wire, the first end moves. So a wire is really something that connects things. Think about electricity wire. An electricity wire connects two things, like it, or whatever other wire. So these spiders are actually generalizations of wires who connect multiple things. So they basically say all these things are now connected together. Well, every leg, every input and output, they're connected together. That's really what they say. And then one rule which governs these spiders, and it's really the only rule, and you can prove this just from their definition, is if you compose a few of these spiders together, then they just form again a spider. Just if I take two pieces of wires and I knot them together, I get a long piece of wire. That's it, really. So in the same way, if you compose the spiders together, and you can prove this from this thing. Now, the important thing is that we used to use them in quantum mechanics. We introduced them actually as a representation of classical systems. We use them as a representation of classical systems and also quantum observables. But here they start to play like a fundamental role in representing things like who. So if you think about a sentence, she who hates Bob, what is this really telling us? Well, it's telling us that there is a female person. That's what she indicates. And then there is also a person who hates Bob. That's what the hates Bob indicate. And basically you're forming a conjunction of the fact that we are dealing with a female person and with a person that hates Bob. So this dot you see there, it's sort of taking in she, it's taking in hates dot, and it sort of conjoins them in that one thing, the female person who hates Bob. So that's what it's doing, really, formally. I mean, the other one I'm not really going to talk about. So again, these are the meanings. Now, these meanings, some of the meanings themselves have wires, and this is again the grammatical structure. How do we get this grammatical structure from a grammar book? There are grammar books like Lambeck's from how is it called? From word to sentence, I think. Yeah, from word to sentence, and then you find in the symbolic way, which I explained before, how these wirings are. So, but it's very nice now that you can really see how these meanings flows in this text. Like it's a very nice depiction of how meaning flow in text, which didn't really exist before. Okay, here's a much more complicated example. Bob gives Claire flowers that Alice does not like. It all still works. It all still works. You can make your sentences as big as you want. The whole thing keeps working. But so one problem we had at the time was that the way you actually put these wires together, the way you put these wires together mathematically, so these words are represented by vector spaces, and the way you combine these vector spaces of in which Alice lives, and in which H lives, and in Bob lives, and actually the tree system inside H, the way you compose them is via the tensor product. The tensor product is a way to turn two vector spaces into one. It's not the only way. There are things like direct product. So if you have two vector spaces, say one of n dimensions and one of m dimensions, if you take direct product, then the joint vector space is m plus m dimensions. If you take tensor product, then it's n times m dimension. So suppose you represent something in 1,000 dimensions or 1,000,000 dimensions, and you see here, out of Alice comes one wire, out of Bob comes one wire, out of H come, well, 3 wires and one is thicker. Let's think about the thicker wire as 2 wires too. So we got 6 wires there. So we got, if we work with Alice represented in 1,000,000 dimensions, which is not a crazy thing, which is what people are doing, and we're talking 1,000,000 times 1,000,000 times 1,000,000 times 1,000,000 times 1,000,000 times 1,000,000. That's too much. You can't put this on a computer. It's too big. So you have to come up with some other trick. I mean, first we came up with some tricks because we have been playing around this computer. And like one way is to come up with, instead of thinking of hates as a monolithic thing, we threw again some spiders at it, like here. So and I'll explain why we do that. Instead of thinking of this box on the left-hand side, now look at this dotted box, and you see some internal structure there. Basically, like you got these 2 dots, what they're doing now is they're copying. So they're copying one wire coming out of H and one other wire coming out of H. And now H is reduced from all these 3, from these 2 thin and this 1 thick wire to actually only 2 thin wires. And that actually made the verb manageable. And it actually is a nice thing because we got this thing here. Then we stick this internal wiring in. Then we do some rewriting. And now, if you look at this picture, it's actually a much nicer picture. It really says we've got Alice, there's a wire coming out. We've got Bob, there's a wire coming out. And then there is this hates thing, which sort of grabs Alice and Bob and connects them together. It really sort of, it's 2 hands of hates. But Alice and Bob, you're now connected by the relationship hate. So it sort of conceptually makes a lot of sense to do it like that. And it's computationally much more economical to do it like that. So we ended up doing things like that, and so you can really think of hates now flowing into Alice and Bob. So people did experiments with these things. They compared this with all existing methods to do lots of benchmark stuff. And this model worked much better than anything else. It worked much better than anything else because there wasn't really anything else who did the same thing, like composing meanings of words into meanings of sentences. So this data is really old now. It's really old now. Still, like once you've got that, you may actually say, yeah, if you do sentences, why not do text? Why not build meanings of entire text? No, I mean, if you can build meanings of sentences, so I'm doing this now. I'm putting two sentences together. Alice hates Bob. Bob likes beer. I'm putting the two together. And again, things become bigger and bigger and bigger. The tensor product is going to make everything exploit. Too big. Becomes unmanageable again. Okay, what now? So we're out of tricks. No, we're not out of tricks. We're going to stick it on a quantum computer. That's the new trick. Stick it on a quantum computer. Because what does a quantum computer do for you? Well, the first thing it does for you is that if this idea of putting these two systems together and putting them together leading to like multiplying dimensions and an exponential blow up, this gives you an exponential blow up in space, it vanishes on a quantum computer. Because for a quantum computer, if you put two qubits side by side, you get this exponential increase of your space automatically. But you know, we were using a quantum model for language. Now, a quantum model, when you start, increases in space exponentially with the number of systems you add. It increases exponentially with the number of systems you add. Classically, this doesn't happen. If you just add, this is not the case, but quantum mechanically this happens. So that's why it was so difficult to put this language model on a classical computer. But of course, it's a quantum model, so it perfectly fits on a quantum computer, and all this exponential blow up is gone. So a second thing we looked at is like, well, I mean, since we're now dealing with a quantum computer anyway, does it give us some more advantages? For example, all the stuff people talk about, like speed ups when you do search, speed ups when you do factoring, and things like that. Do you get something like that? And it turned out for the sort of typical tasks you want to do with natural language, you get all these quantum speed ups too. Now this, what is this, 2016? In 2016, there weren't any really decent quantum computers around yet. There were quantum computers around, but nobody would ever think to do natural language stuff on them. I mean, they were so small that you couldn't do anything serious with that. Okay? Still, we did start thinking about what you could do with them at a time, and the sort of thing we had in mind that would give you speed up was question answering. So I'll just keep it simple here. So how can you think about a question in these diagrams? Well, this was so basically. So I had this representation of Alice hates Bob. Alice hates Bob. So what I'm doing now is I'm just replacing Alice with a black box. So, and I can think of this as the question, who hates Bob? I mean, I haven't put Alice there yet. So this is like, there's a hole, like, what should I stick in a hole is the same as who hates Bob. That's like a nice representation of who hates Bob. So that's a question. That's a question. Who hates Bob is a question. Now, if you got a question, you may want to answer this. So I've got some more. I'm going to skip. I mean, you can ask other questions. Like this one would be, who does Alice hate? Who does Alice hate? Like I throw away Bob. Who does Alice hate? I'm going to skip the next few ones, like this one and this one. Not important. So okay, let's go back to the who hates Bob. This one. So how do you answer that? You see what I did is I put two dots on the outputs. I don't know whether you, so you see there's two extra dots on the output, so I close these down. Now, a diagram like this, without any outputs, is a number. That's a number. And the number, I mean, I can represent this a bit different, like what I'm going to do here. You see on the top line, so these spiders, they fuse together. I already explained before that they are like wires, so you can just fuse them together. And then you get the picture in the middle, and then you can sort of slide these two boxes, question mark box and Alice box, towards hates. So what you see on the right hand side is really an inner product. You got an inner product between hates and question mark tensor Bob. So that's an inner product. So when is an inner product maximal? An inner product is maximal whenever the thing at the bottom matches the thing at the top as good as possible. So what we're actually looking for is a pair of something together with Bob which matches the word hates as good as possible. So this would actually be whoever hates Bob the most. Whoever hates Bob the most is going to maximize this. And it turns out that for this problem, figuring out who hates Bob the most, you get a quantum speed up. It's an instant of a standard quantum algorithm. And what this quantum algorithm does is given a bunch of vectors, it looks for the vector which is closest to a particular given vector out of a bunch of vectors. And that's really what we need here. We just need the word which fits that, which fits the something hating Bob the best. So these are proper quantum algorithms, very simple. You don't need any very complex math or number theory to explain this. This is a very simple question answering thing which gives you a quantum speed up. And this is of course a very natural task in natural language, dealing with natural language. And there are many variations on this theme, which also would give you a quantum speed up on a quantum computer. I'm going to skip that. Right. So I'm going to so with Will Zhang, here we had this idea to stick it on a quantum computer. I mean, it's bloody obvious that you want to stick something which is a quantum model on a quantum computer. Like in practice now, the thing in, say, quantum industry, which is the closest to actually revolutionizing stuff in the world, is quantum chemistry. It's quantum chemistry. It's like basically simulating chemical molecules and stuff like that on a quantum computer, because I mean these chemical molecules, they're quantum things. If you try to simulate them on a classical computer, you got the same exponential blow-up I was talking about with this language model. It's the same thing. So now people are already doing this on quantum computers, and this is starting to actually become close to fruitful. Something that in not too many years, maybe 2 or 3, you couldn't do on a classical machine anymore. So that's really where quantum computing is now really happening for like chemical stuff and stuff in materials. So that's what most of the quantum companies are now focusing on, and that's where most of the other businesses are like starting contracts with quantum computing companies for chemistry. But this natural language stuff is, I think, an equally big potential, because it has this quantum model underneath it. Okay, so this is a generic quantum computer. That's generic quantum computer. Now there is no such thing now as a generic quantum computer. There are particular quantum computers, and they all have different hardwares, and they're all pretty small. And there is a name for this, and so that was the thing I disliked. They call this now NISQ quantum computers. So what does NISQ stand for? The N stands for sort of near-term stuff. So there is no error correction going on. It's small scale, and there are a lot of limitations. Like one of the biggest limitations. So when people teach you about quantum mechanics, then the first thing you learn, or one of the first things you learn, is if you got a quantum state, you cannot just read this quantum state. You cannot just figure out what it is. You have to measure it, and then you disturb it. So while in your quantum memory or whatever, you can have lots of information, and you can actually do computations in parallel, like millions of computations in parallel, you can't read the outcome. Just like that. You have to do special tricks to learn something or even anything about what happened in a quantum computer. Turns out that the same is the case today to put something in a quantum computer. You can't just take a bunch of classical data and stick it on a quantum computer. It doesn't work. Whatever benefit you would get out of your quantum computer, you already lost. It's already gone. So there is sort of this theoretical idea of something called quantum RAM, but it doesn't exist. People haven't built it yet. I mean, you could think, okay, yeah, that's the end of it, but it turns out not to be the end of the story. You can actually, there are clever ways to actually, one way or another, getting your data on a quantum computer without just sticking it in memory. And so this paper, which I show here, is really about how can we put this you can do this natural language stuff on a quantum computer, avoiding the idea of assuming that you can just stick it on it, so which doesn't work. And I mean, there's a paper forthcoming, like next week, hopefully on the archive, which actually gives a lot more details and like a conceptual foundation on that. So this is the work we have been working the last year on, trying to put these things on a quantum computer effectively. And so we came with our ways. And this is something, I mean, there's a few things. Like, I was just talking about sticking things in a quantum computer. Then the other things, let's go. A quantum computer doesn't understand, for example, this picture. The quantum computer doesn't understand this picture. Why doesn't the quantum computer understand this picture? Because the quantum computers which are around now, they only understand circuits, quantum circuits. So a circuit like with gates, I mean, classical circuit has like AND gates and OR gates and NOT gates and stuff. Quantum computer is a circuit. It's like a linear circuit. It's like a reversible circuit, all unitary reversible stuff. And it has things like C0 gates and then some other phase gates. And this doesn't look like a bunch of like circuit gates. So what we use now is another thing. Oh, go forward, which we call ZX calculus. ZX calculus is based on spiders, like I described before, but spiders of two different colors. So with these spiders of two different colors, you actually can provide a full alternative to linear algebra. So the usual formalism of quantum mechanics is linear algebra, but you can get like a valid alternative where you can do all equational reasoning that you can usually do with your linear algebra purely with diagrams. And this is what is provided by the spiders of two colors, and that's what's called ZX calculus. ZX calculus. So that's what we use. So we're basically going to use this calculus, which is diagrammatic calculus, to turn the language diagram, something like that, in a quantum circuit. So you start with some language diagram. Well, I popped out some spiders of a different color. As it turns out, what you see now is already a big step forward, because you see this horizontal line between a white and a red dot, and that turns out to be a C0 gate. So that's a C0 gate. That's something a quantum computer understands. And you see two C0 gates here. And then, okay, we do some more juggling, and it doesn't matter. But this is actually the quantum computer. We just compiled this language diagram to a quantum computer. This was the compilation. We just compiled it. And this stuff we can actually stick on a quantum computer. So this stuff, what you see here, is really a quantum computational interval circuit implementation of the sentence Alice hates Bob. So, and we use this ZX calculus stuff to do this translation. So this is what we just did. So that's compilation. That's what we would call compilation in standard computation. Like going from something high level to something like machine code. That's machine code on the right. That's quantum computational machine code, really. And now comes so we know how to translate our language diagrams to machine code. And you see in this machine code, there is all these variables, alpha, beta, gamma, which are actually representations of or things which are directly related to the word Alice, to the word AIDS, and the word Bob. Now, I told you there is no way to store the meanings of Alice and Bob and AIDS directly. What you can do, and this is really like where proper machine learning comes in here, even if you don't like it, whatever, it comes in here. So what we do now is we train these variables. So these variables are not quantum data. They're really settings on your knobs on your quantum computer. They are knob settings of your gates. They're not sort of data in the quantum computer, because you can't get, like I said before, these things efficiently in the quantum computer. So you're going to do some machine learning. You start off with some setting, then you do some computation. You see whether this is really what you want it to be. You adjust your variables, and you do some learning, and it turns out you can do this efficiently. This is an efficient way to get your meanings on a quantum computer, but you use some machine learning here. So you learn the settings of the variables. Okay, I mean, is that a theoretical idea? No, that's not a theoretical idea. We did this for the first time effectively on a quantum computer. We used a corpus of 16 sentences then. We used 8 for training to actually get the variables inside, 8 for testing, as in we asked questions. So once we trained the machine, it had some knowledge. The knowledge was 8 sentences, not a lot. And then based on these 8 sentences, we asked some questions to the machine, asked 8 different questions. I mean, the sort of, so the corpus we had like words: Romeo, Julia, love, skills, dies, who. And then the sentences were something like Juliet kills Romeo, who dies. I mean, I don't think she ever did that. But so this was a question we asked, and of course the answer was no. No, she loves him. She didn't kill him. So that was an answer we got. We got no, because we pretty much did yes/no questions mostly, because it's simple. Meanwhile, we work with like corpus of 100 sentences. So we use 100 sentences for the computer, maybe 80 for training, and 20 questions or something like that. So we are really doing that now on quantum computers. We are doing some natural language processing on actual quantum computers. This was all done with the IBM machines. So like a real experimentalist, you get then data and diagrams, like how does the theoretical prediction goes with like the effective. This is how well the training process worked actually, and it all matches the experimental stuff. So I mean, it's working all very well. So this quantum natural language processing is now a real thing. I mean, I think I'm pretty much running out of time, so maybe I should just leave it for questions. Let me just scroll through whether there is really something important to say here. I don't think so. So, I mean, this is like a summary, like what combines grammar and meaning at the start is a quantum model. What is classically exponential, which is like all this composing, becomes a free lunch, because so the way people get this data on quantum computers now, the only way they can do it, even if is via the circuits that you train, and lots of people are doing this without these circuits having any meaning. In our case, these circuits mean grammar, they mean language structure. So they actually have a meaning. So this language structure, if you try to do this on a classical computer, is exponentially expensive. If you do this within this paradigm of these circuits already being there, it comes for free. So that's cheap. Yeah, I mean, all this is not so important now, not so important. So I've said all of these like algorithms. So we are starting in Oxford a team, like I say, next week, under the umbrella of CQC, dedicated to this quantum natural language processing, quantum AI more generally. So when we started all this diagram stuff, 2003, 2004, everybody was laughing at us, like, that's all good for kindergarten, but it's never going to lead to anything practical. So I mean, I told you one practical thing. Another practical thing is that this ZX calculus now it sets the state of the art for quantum compiler optimization of quantum circuits. So all this diagrammatic stuff is becoming pretty important in quantum industry. And you can learn this from all the people in our group, and you can learn this from these people at the Oxford CQC, and so on. And I think I stop here then. Okay, thank you.
Okay, thank you. It was a really interesting talk, and then we have Q&As now. I will start with one question myself out of interest. So about one point. So like those different diagrams that you make for the sentences, for example, you want to give it to a computer for it to learn. Do you make the diagrams yourself, or does the computer make the diagrams?
So you use parsers for that. So this is technology which already existed. If you feed a piece of text to a classical computer, then they start tagging it with grammatical types. So they figure out what are the names, the nouns, what are this, what are that. And then once you got that, then all the rest follows. Then the sort of derivation, assuming that all these things are well formed, then the computation I was doing on the blackboard is exactly what the machine does, and it gives, and the result is the diagram. The caveat here is that these parsings are not always deterministic. There may be ambiguity, there may be different interpretations. Like I'm giving you an example of something, black metal fan. Black metal fan can be a person who likes black metal, or can be the fan on the stage of the black metal concert to sort of cool down the musicians. And they even have, these two phrases have different grammatical structures even. Because first you bring black and metal together, you apply it to fan, And then on the other case, you got your fan, which happens to be black and which happens to be from metal.
Yeah.
So they even parse differently. So there you have a superposition of two different diagrams, and you have to then handle. The only way to figure this out is to see at a wider context. So if I say the black metal fan stands on the stage, it doesn't teach me anything. Yeah. Washing the black metal fan, yeah, probably it's a device.
Yeah. So with more contextual information, you can.
Contextual information.
Yeah.
It is ambiguous.
Yeah. Okay. And also.
True for word meaning and grammatical parsing both.
Yeah. Okay. Okay, we have quite a few questions, so I will start with the first one from the Q&A, and it's from Brett, and I can ask him to answer live if he wants. Or maybe, no, it will be too hard. I will just ask because we have quite a few questions. Okay, when do you think there will be a real quantum advantage to quantum natural language processing? Is there any advantage, even if slower, because more complex sentences can be analyzed in classical?
Right, so that's a very good question, of course. I mean, you probably know that where was it, a few months ago, Google did something that practically can't be done on a classical machine anymore. Now, this wasn't a very useful thing at all. Definitely had nothing to do with language. So there are different stages. There is sort of doing something in a classical machine that on a quantum machine you can't do classical. Doing something in a quantum machine you can't do classical, and you can explain what you actually did. So meaningful, something meaningful. And then the third stage would be doing something practically useful, which is still different from meaningful. My estimate is that we can already do something meaningful that you can't do classically. So the sort of thing we have in mind is let the quantum computer generate some language itself, like some artificial language, like let the machine invent some language, and then start doing question answering with that. So imaginary language, that would be something that would be incredibly difficult to do on a classical machine if you do this large scale enough. And that's probably possible to do on a quantum machine now, or definitely within the next year or two. So of course, that may be not that practical. That's kind of cool for video games and stuff like that, or something like that. But then going to something that actually practically will push you into the market and replace all the other stuff, I would say 3 to 5 years.
Okay. Hopefully that answers the question. Okay, we have a question from Edward. I will allow him to talk if he wants. Let's see if anything responds. If not, I can just ask the question.
Microphone is off, Edward.
Oh, okay, I can ask the question. Then why does quantum mechanics prevent certain copying operations on qubits? Why is the no deleting theorem the time reverse of non-cloning? It's in the chat if you want to read it again.
Well, no cloning. The cloning is one of the. It's just linearity. Like once you move. We think of no cloning as something weird for quantum mechanics, but like cloning is really something that only can be done with Boolean information. If you think about probability theory, like a coin flip, you can't copy a coin flip neither. If you flip a coin and you make, which is like an unbiased coin, and you copy that coin, you imagine like that same thing happens twice, then you don't have two independent coin flips. You've got two perfectly correlated coin flips. So they're not very useful because once you've done the first one, you know what the second one is going to do. So the no cloning is not like sort of a mysterious thing. It's more a surprise that in classical Boolean word, you actually can clone. And just like with the probabilistic stuff, like quantum mechanics, you can't clone. Why is that? Just part of the linear structure, and like I just explained, it seems that more things are not clonable than things are once you go to more general mathematical representations than Boolean data. There is also like, this is time symmetric because it's really a property of linear algebra. This is all time symmetric. The deleting is sort of a more subtle thing, but the real thing, I mean, this is stuff we teach in our course, of course, which you can read about in our book, of course. So the more subtle thing is that there is something which distinguishes quantum mechanics from probability theory, and that's called no broadcasting. And that's a lot more subtle than cloning. This is if you got something and you make two copies and you ignore one copy, is the thing you get still related to the input? And for both. And that's something you can do with probabilities, because if I copy my coin flip and I look at one of the two, then it's still like an unbiased coin. And if I look at the other alone, it's still an unbiased coin. It's only when you look at the two together that they are correlated. So it turns out this is something. So even quantum mechanics, it's different. You can't even do that. So in quantum mechanics, you can't even do copies which on their own behave like the original. So that's the real property which is interesting, not the no cloning. Because that's pretty much applies to anything.
Okay. Well, we have quite a few questions. I know we will be able to get all over them, but let's. Okay, one from Q&A. How do the ideas of quantum natural language processing translate across different languages, where grammar structures might be drastically different, or do they simply correspond to different arrangements of the spider diagrams?
So, well, yeah. I mean, if you think, I mean, let's just think about. So I showed this picture like of a Alice hates Bob. So you got like this a couple on the left, a couple on the right, and a straight wire in the middle. So this topology stays the same, but it may be. So here we've got first the subject, then the verb, then the object. So for any permutation of these three, subject, object, verb, there is some language in the world where you have this order. So there's some languages where you got subject or verb, you can have verb, subject, object. Some are very common. Then one of the 6 permutations only spoken by 30,000 people in the world or something like that. But so the order changes, but the connections stay the same. There will be a wire going from the subject into the verb. There will be a wire going from the object into the verb. And the funny thing, so, and the algebraic gadgets, the mechanisms stay the same throughout language. It's just the word order which can be different and some other little properties which can be different. But the general idea of this sort of algebra structures stay the same. Now, what is an interesting thing is I was showing you how you go from this sort of typical Chomsky-like structures and Lambic-like structures to circuits. Once you move to circuits, the differences between languages vanish. So in the circuit form, the language differences are gone. These orders are all gone. So that's kind of an interesting thing we're playing around with now. It seems that there is something more universal than the language we humans speak. Now, the deep philosophical reason there is we humans are very poor creatures. We can only speak one-dimensional. We can only produce one-dimensional strings of sounds. Now, once you got these language diagrams and you allow yourself to deform them and to depict them as two-dimensional circuits, this is something we can't speak anymore. This is not something we can hear anymore, but you can look at it and we know what it means. So it's sort of our limitation on how we can speak and hear that forces the language to be that one-dimensional, and where the differences of language come from. It's bureaucracy where we have to make a choice. Which are we going to put first, subject or object? Where are we going to put the verb? And different choices that we made in different languages. I mean, just to give you an example, I love you in English version, je t'aime in French. The French je t'aime, verb is at the end. I love you, the verb is in the middle. So, but they mean the same, the wires are the same. If you go to the circuit, they become the same.
Okay. Is it possible to create language models like BERT and NISQ computers? If not, what would it take to create these algorithms in quantum computing? I'm not sure what BERT is.
So yeah, BERT is one of the sort of more successful NLP type of engines now and mechanisms. You got this transformer things, all that. You got GPT-3 and things like that. So basically what they do is they don't use grammar. They try to infer grammatical structure. They don't take grammar as a given. And part of the reason of that is there's two reasons for that. Like it's very expensive to do that on a classical machine, like I said. So whenever they tried, they didn't really get very far because it just, I mean, it doesn't really work very well on classical machine because it's too expensive. And secondly, also these ambiguities I was mentioning earlier. If you don't have the right machinery to deal with them, then it becomes also super expensive. So they mainly have very clever tricks to work with these passing ambiguities by guessing the next word in the right way. So they have a very smart algorithm of guessing grammatical structures and guessing the next word. And that works pretty well. And on a classical machine, it's kind of hard to think how you're going to come up with anything much better in short term with these things. If you go to a quantum machine, you are allowed to actually take this grammar as given. And these ambiguities I was starting to, classically, this means going from non-probabilistic stuff to probabilistic stuff, which is a huge step. It's a huge step computationally. It's very expensive to go from non-deterministic to deterministic to non-deterministic, from bits to probability distribution. Quantum mechanically, it comes for free. It's just there. This sort of it's called mixed state density matrix. This sort of mixed knowledge is just part of quantum mechanics. So this ambiguity comes for free. So yeah, I think on a classical machine, doing better than stuff like BERT at the moment with available hardware is impossible. Like, I mean, computers have to become exponentially large just to even compete with them in a proper way, I think. But on quantum machine, that's exactly where this sort of things I was talking about are feasible.
Okay. Where's the question? I think there's this question related to complexity theory. How long do you think it approximately may take to able to solve NLP problems at the level of complexity that we have now in classical computing?
Wait, I can't. Can I read it? How long do you think?
It's in the chat. Yeah.
And on the level of complexity that we now. Oh, you mean, okay, it means like equally complex NLP problems. Okay. I mean, my guess is like the first things that are going to happen will be different problems. I mean, I think when you go to a different hardware or a different context, like what we're trying to do here now, it's always a bad mentality to try to do the same stuff as you do on other hardware or you do with other tools. I mean, if you got a hammer and then you discover there is something like a screwdriver, you're not going to try to make the screwdriver do better at what a hammer is very good. Like, I mean, you can try very hard, but you're not going to nail the nail better with your screwdriver than with hammer. And I think we should think like that about the use of quantum computer too, because we've got this ability to make some things explicit, very explicit now. These ambiguities, this composition of systems, encode grammatical structures explicitly, together with their ambiguity. And so the thing to go to is like meanings of large text. And one place where I think that this can be very useful is generation of language. Because if you generate, then it's very good that you got it as much as a given as possible. Like if you understand grammatical structure in advance before you start speaking, that's very useful. Much more useful than while you're speaking, you actually have to figure out what grammatical structure is. Which is very hard because you got no context, because you're the one who's speaking. It's very hard to figure out what grammar is, like Bert is doing now, if it's you who is speaking and it's you who has to figure out what to do. So most of current NLP is like analyzing language. And I think this stuff will be first useful for actually generating language.
Okay. Okay, it's quite a nice question. To a person in computer science and linguistics, what advice would you give if we are interested in your study area?
So I mean, now I'm parsing the meanings there. So what do you mean by interested? As in like career-wise or reading a little bit or?
I'm not sure, it was not specified. But maybe just.
You want to do a master project? See, I can interpret interested in that.
Yeah. We can move on.
It will be very different depending on the qualification.
Yeah. Okay.
Maybe I can answer this. Like, I mean, if you're interested in doing a master project or something like that, just come to us. Like the quantum group in computer science, we supervise people not just in computer science, also in physics and maths and other departments. Happily, we're always happy to supervise people. We got a lot of people. If professionally you want to sort of do this thing, like I say, like I mean, you can start trying to do a PhD, or you can come work with like the company Cambridge Quantum Computing, which now has a team. So people who are studying still and doing master thesis now at Oxford have already approached us, and we even have already awarded conditional job offers and stuff like that. So that's the job. And I mean, if you're interested in this sort of stuff, quantum industry, I mean, Ross didn't show up here, but I mean, you can just write the companies, like you can write Cambridge Quantum Computing, and then we'll get all your CVs, and then, yeah, we're always hiring. We just hired 25 people, and we're going to hire another 25 in the next half year or so. So we're always looking for very good people.
Yeah, probably that's good to hear for people. And like, how big will be your office in Oxford?
But you mean my personal office will be much bigger than any university professor's office.
Yeah. Yeah.
I mean,
not literal, like about the people working.
we're starting with 20.
Okay.
We're starting with 20, but we got space to expand to 40.
Okay. Yeah, that's quite big. Okay. Let's do a few questions and then end the talk. So like, if there are applications of QNLP in the near future, what do you think the most promising direction is? Is QNLP likely to contribute, example, to translating text through common grammar or to sentiment analysis?
I mean, sentiment analysis is the sort of thing which doesn't work very well at the moment. So sentiment analysis is very much like a classification problem, like I was just like showing, like with the algorithm. So sentiment analysis is definitely a clear candidate. So the way I think about this is this formalism is much more meaning aware. It's much more. So a lot of the machine learning now, NLP machine learning is sort of whole black box. It works well, but you don't really know what's going on. So wherever there is a big advantage to actually better understanding that's what's going on, that's where you're going to get much advantage. And I think sentiment analysis is clearly something you would expect that, because it's quite a subtle question, like what is the sentiment in this thing? So you really need to, I mean, if it's a big text, you really need to understand the text as a whole. And there aren't any real tools now to do that at all. I mean, the translation is also pretty bad, by the way. So we're actually talking to like a very well-known mobile phone company at the moment, and they're working directly with our team, specifically on translation, and see whether not tomorrow, but like say 5 years, we can actually come up with a much better way of translating using our method. So we're doing this now. Oh, is Ross there? Okay, yeah, you can come in. I announced you, but I was just talking about jobs and stuff like that. And now the blackboard is falling down. He's pushing the blackboard from the wall. Roscoe is critical to say he always wants people for jobs. He's looking, he's looking for people to work in his team, developing quantum software, quantum compilers, and they do a lot of stuff. They work directly with quantum chemistry and all that. So he's always looking for good people.
Yeah, but what kind of background are you looking from?
I'll type the name.
In terms of people, like what's the main background?
Well, in my team,
yeah,
they're a big mix. I think the biggest minority is people with like a straight up quantum computing background. But we have some people who are software engineers from classical world. We have some people who are theoretical chemists. Yeah, a few other kinds.
Yeah.
Yeah, I mean, in my team, I've got pure mathematicians. I've got like quantum foundations people, like really doing PhDs in quantum foundations. Pure category theoreticians. I mean, just good people. I mean, the way I think about it is everybody has to learn a little bit of everything. I mean, there's also somebody who had a career in practical NLP, of course.
Mhm.
So it's a big mix. It's a big mix for me. I mean, very broad.
Yeah. Okay. One question was, is there any software package to encode text into quantum gates and circuits? So like probably accessible to the public.
Don't you guys make them?
Well, we are building that. We are building that. But so what they for example do is like take gates and then turn this into other quantum gates which are much more economical. And that's really where you use the spiders for. You really use the spiders. So, but yeah, I mean, we are building it at the moment, like from language to circuits. I mean, it kind of already exists. Like there is one actually which exists already. It's called, okay, I'll type this down. Disco Pi. Disco Pi. It's something developed by 2 people of my team. So, okay, this is Ross's name.
Mhm.
And now the software you can play around with. And if you ask Alexis Toomey about this, he'll be very happy to help you out playing around with it. So it's online available. You find this Disco Pi, and it's constantly developed. And this actually turns like a language into circuits. It's more like a toolbox at the moment.
Okay. Okay. And the last question, is there some way to quantify how well we can compress the meaning of a text? For example,
when I type something, it went to all panelists, so I have to actually write this again. I get complaints here, but let me write this again. Everyone, all panelists and attendees. That's what I have to type. Okay.
Yeah.
Again, you got it now?
Yeah.
And here is Disco Pi. There.
Yeah. Okay. Again, the last question, is there some way to quantify how well we can compress the meaning of a text? For example, how many words would we use to represent the meaning of 900-word text?
I mean, that's a very good question. That's a very good question. We haven't actually done much with, I mean, these are important questions even to understand quantum advantage. It's not just about compressing, but it's how much does the entanglement is irreducible to some sort of classical context.
And how much you can resolve it tomographically at the end as well.
How much you can resolve things tomographically. These are very difficult questions. And we haven't gone that far with that at the moment, I'm going to be honest. Like, these are very hard questions. The sort of idea of like representing text in the way I was describing is just 1.5 years old. The entire idea because for many years we knew how to compose meanings of words into sentences and it ended there. So the sort of the ability to go to text via circuits is very recent. So I've got now a bunch of PhD students working on that because it's still very much in the academic level.
Okay, great. So let's end it here. Really, thank you for your talk. We had many people attending. We had like at some point 50 or 60. I'm sure everyone enjoyed your talk. And then, yeah, thank you again for talking today.
Thank you for having me.
Nice to meet you.
Okay.
Bye.
Yeah. Bye.